So to recap what we did in the previous lecture, we looked at the range, we looked at the standard deviation of a sample and population, and we looked at the variance of the sample and population. So this is what we looked at for spread. We're going to look at another measurement of spread, which is called interquartile range, but first we have to add a few more things to our repertoire. We talked about the range rule of thumb. We talked about the empirical distribution, which is also known as the 68, 95, 99.7 rule. And we talked about the coefficient of variation, which is a way that we can compare very different distribution. In the next section, we're also going to talk about things that help us compare individuals or scores from very different distributions, and those are called z-scores. Then we're going to talk about percentiles, where we take our data and we divide it into 100 equal parts. We're going to talk about quartiles, where we take our data and divide it into 4 equal parts. And then using quartiles and the range, we will make box plots. So a z-score is what statisticians call a standard score. And what that means is we change the scores from a raw score to a standardized score. And in that standardized score, we really are just talking about the number of standard deviations above or below the mean. This is a way we can compare things that have large standard deviations to things that have small standard deviations and be able to tell if they are unusual in their distribution. When we do a z-score, we take our individual score and we subtract the mean, and then we divide it by the standard deviation to change it into standard deviation units. When our score is larger than the mean, we get a positive z-score. When our score is smaller than the mean, we get a negative z-score. We will be using this formula for sample z-scores. You can do the same thing with population parameters, but you don't usually do that. We will round z-scores to 2 decimal places when you calculate them, and we do this because it becomes important to us in Chapter 5. Now, we talked last time about usual or ordinary values and unusual values. And we said they were unusual if they were 2 or more standard deviation units above the mean. And so when we standardize this is exactly what we're doing. We're talking about the distance that a score falls from the mean. And ordinary values are in this blue part of the distribution. They are within 2 standard deviation units of the mean. And remember our 68, 95, 99.7 rule. About 68% of the data fall in here. And then our unusual values are going to be more than 2 standard deviations above the mean, or less than a negative 2 standard deviation units below the mean.
And it says data set 16 in Appendix B lists 50 magnitudes on the Richter scale of 50 earthquakes, and those earthquakes have magnitude with a mean of 1.14, and a standard deviation, and this is a sample, so our standard deviation will be S, of 0.587. And it tells us that the strongest earthquake, which is the maximum value, has a magnitude of 2.95. So first of all, it says, what is the difference between the magnitude of the strongest earthquake and the mean? Well, we can calculate that. That'll be 2.95 minus 1.184, which will be 1.766. And then B says, how many standard deviations is that? Well, we're going to do 1.766 divided by our standard deviation, which is 0.587, and that comes out to be 3.01 standard deviation units. Now, C says convert the magnitude of the strongest earthquake to a z-score. So remember, our z-score is my score minus the mean divided by the standard deviation. So the score I'm interested in is 2.95. I'm going to subtract the mean, which is 1.184, and I'm going to divide by 0.587. And you can see that's just a summary of what we did in sections A and B. So our z-score is going to be 3.01. So z equals 3.01. And so when you do z as 3.01, you don't have to describe it as 3.01 standard deviation units because you know that. Then it says D, part D says, if we consider usual magnitudes to be those that convert to z-scores between a -2 and a +2, is the magnitude of the strongest earthquake usual or unusual? An earthquake of magnitude 2.95 is unusual. And I'm going to say z equals 3.01. And that's how you would do a problem like that. Now, let's compare a couple z-scores. Let's look at number 15 on page 146. Okay, it says, as of this writing, the tallest living man has a height of 247 centimeters. So let's call him a man, so we'll use the biological symbol for man. And his height is 247 centimeters. The tallest living woman has a height of 236 centimeters. Now, the distribution of the heights of men are going to be normal with a mean of 175 centimeters and a standard deviation of 7 centimeters. While the heights of women are normally distributed, and they have a mean of 162 and a standard deviation of 6 centimeters. So, relative to the population of the same gender, who was taller? So we want to know, is our man or a woman taller comparatively to others in their gender? So let's go ahead and standardize this. So I'm going to standardize our man first, and my score is 247 and my mean is 175, and then my standard deviation is 7. When I do that, I get that his z-score is 10.29. That is a long way from the mean, isn't it? Now let's look at her z-score, and that's going to be her height minus the mean divided by the standard deviation, and that's going to come out to be 12.33. So because she is further from the mean and standard deviation units than he is, then our woman is relatively taller than the man. And we can summarize that as 12.33 is greater than 10.29.
When we talk about measures of precision, one that you've all had experience with are percentiles. And percentiles just tell you where your score sits by the percentage of the distribution. So if you get in the 80th percentile on your Iowa Test of Basic Skills reading, that means you scored better than 80% of the people who take the test. If you score in the 50th percentile, that means you are dead on average. A percentile is not the same as a percentage. And a 50th percentile score is pretty good. That means you're spot on average. Where if you score 50% on a test, that's not a good score. How do I find the percentile of a data value? You put them in order, you count the number of values less than the score you're interested in, divided by the total number of values in the data set, times 100 to make it a percentage, and then that gives you the percentile value. L, again in this case, is location. So if you want the location of a certain percentile, we use K to stand for that. You take the percentile that you are interested in divided by 100 times the total number of values in the data set. That gives you the location or the position of a certain percentile score. Here's a flow chart that you can work through on your own. This is also found in your textbook on page 135. Now, another set of measures of position are called quartiles. And I will say this may be one of the more useful measures of position that we're going to use for quick data analysis. We will be using z-scores extensively later, but when we just want to get a quick picture of the data, quartiles work. And so we have the first quartile, in which 25% of the sorted values are below that. Quartile 2 is the same as the median. We already know how to find that. We did that in section 3.2. And then we have the third quartile, which in essence is the median of the top half. And here you have a graphic representation of that. Now, this is the weight data that we looked at earlier in the course. And remember, these are 63 individuals who were in an introductory stats class on the first day of class, and we recorded their weights. And remember, to find the median, we take the number of individuals plus 1 divided by 2 to find the location of our median. So we have 53 individuals divided by plus 1 divided by 2 is 27. So our median is our person right here that weighs 165. Then we ignore that score and we look at the bottom 13 individuals. So it's the 26 who are lower than that, plus 1 is 27, divided by 2 is 13 and a half. So we are looking for the number that's halfway between the 13th and 14th individual. And so halfway between 127 and 128 is 127 and a half. That's our quartile 1. And we do the same thing counting from the top. So we're going to count from the top 13 individuals. And we're going to find that it's halfway between the 185 at the top of the 5th column and the 185 at the bottom of the 4th column. And of course, 185 plus 185 divided by 2 is 185. So now we have our 3 quartiles. So we know that half of the data is going to be between 127 and a half pounds and 185 pounds. We know that half the data is below 165 pounds, and we know that half the data is above 165 pounds. We can look at that in our stem and leaf plot. We can do the counting in the stem and leaf plot. And so our quartile 1 is going to be right here between 127 and 128. We know that our median is our 165 right here. And we know that our quartile 3 is right in here. Now, other things that we're going to talk about is the interquartile range, and that is a good measure of spread because it tells you where the middle 50% is when you use the 5-number summary, which is your 3 quartiles, the minimum and the maximum. Then we have the semi-interquartile range, which is the same as the mid-quartile range. I'm going to tell you I've never used these, but they're there. And then you have your 10-90 percentile range. Again, I've never used that. The 5-number summary is a good set of descriptive statistics that you'll want to use when you have skewed data. And the 5-number summary consists of the minimum, quartile 1, the median, which is also quartile 2, quartile 3, and the maximum. And there are your 4 numbers. And so again, I know that half my data is between 127 and a half and 185. I know half my data is between 100 and 165. I know half my data is between 165 and 260. And look, I can think about this. From 165 to 100 is 65. From 165 to 260 is 95. So because the distance that is covered by those individuals that are half the data set is bigger from the median to the maximum, I know this will be skewed to the right. Now, again, that interquartile range, the distance between quartile 1 and quartile 3, is a really good measure of spread. Remember when we had the bell-shaped distribution, we said that there is 68% of the data is within 1 standard deviation of the mean. Well, that's kind of like here. We're saying half of the data is in these 57.5 pounds from 127.5 to 185. And we can use a 5-number summary to draw a box plot. So if we draw a box plot for the weight data, the first thing we need is we will draw a box that spans from quartile 1 to quartile 3. We're going to put a line in the box that marks the median, and then we're going to draw lines out from the box to the minimum and maximum. So here's an example. First we need to have a scale, and it's a uniform scale, and we will draw our quartile 1 at 127.5. Now, the length of this line does not make any difference. It's the location of the line that's important. We're going to put in our quartile 3, which is 185, and make a box. Then remember, our median was at 165, so we're going to draw that in. And so this shows us about the middle half of the data. You can see, now think of these as people. You can see that the people who here are between quartile 1 and the median have more room than the people who are here between the median and quartile 3. That's another idea that tells us that we don't have a uniform distribution. We don't have a normal distribution. This gives us that information. So there's our box, and a box plot's also called a box and whisker plot. So now we are going to draw the minimum and a line to the box, and we'll draw the maximum and a line to the box. And notice how from quartile 3 to the maximum is longer than quartile 1 to the maximum, that's another indication that this is a skewed data set. Now here are some other box plots showing you similar things. We have box plots of movie budget amounts, and I would assume that these would be in millions of dollars. Here's the box plot of a normal distribution, which would be that symmetrical bell-shaped curve, and you can see how things to the right and to the left of the median are exactly the same. There's no difference from our lower whisker to our upper whisker. And here's a very skewed distribution. Now, let's talk about outliers a little bit, because we can deal with outliers in a box plot very easily. Now, why are outliers important? Well, we know that outliers cause trouble when we're dealing with the mean. They have dramatic effects on the mean. And because we use the mean to calculate the standard deviation, outliers affect the standard deviation, because remember, the mean and the standard deviation are not resistant measures. And they can make a big difference on the scale of our histogram. Now, when we are doing box plots, we look at that interquartile range, and if we have a data value that's more than 1.5 times the interquartile range above quartile 3, or 1.5 times the interquartile range below quartile 1, we count those as outliers. Now, what we do then is we use a modified box plot. And what a modified box plot does, it puts a special symbol in for the outliers, and then it only draws the whisker to the data point that is within the 1.5 times our interquartile range. So here is a modified box plot. It has to do with pulse rates of females in the data set, and you can see that we have two individuals, this one at about 105 beats per minute, this one at about 125 beats per minute, that were more than 1.5 times the distance from our quartile 1 to our quartile 3. Now, we've talked about z-scores. We've talked about usual and unusual values with z-scores. Remember, it's unusual if it's 2 or more standard deviations above or below the mean. We've talked about percentiles when we take the data and divide it into 100 equal parts with the same number of individuals in each part. We talked about quartiles where we divide it into 4 equal parts of numbers of individuals. We talked about changing a percentile to a data value. We talked about some other statistics. The one that you want to remember here is the interquartile range. We talked about the 5-number summary, and we talked about how we use a 5-number summary to make box plots, and we talked about the effects on outliers. Now, outliers affect the mean and the standard deviation because they are not resistant measures. When we talk about the 5-number summary, outliers don't affect that very much other than the range. And so the median is a much more resistant measure of center than the mean. So when we have outliers or we have skewed data, the 5-number summary may be a better summary than the mean and the standard deviation. Let's remember what we're going to do. Whenever we deal with data, we talk about where did the data come from. We talk about the context and the source. We talk about the sampling method. Is it worth looking at it, and is it worth analyzing? We talk about measures of center. We talk about measures of variation, and we look at the shape of the distribution. We look at outliers. If we're dealing with a time series, we look at changing patterns over time. What conclusions can we draw from this, and what practical implications does our data give us? And remember, shape, center, spread are the things we want to look at when we're describing the distribution. And so that takes into account measures of center, measures of variation, description of the distribution, and outliers. Now we're going to talk about the active question.